All right, in this exercise, we're going to amend or change our primary production code, which you can see right here I've got loaded from our last exercise. And we're going to add to it, and we are going to add both a nutrient field and growth rates. We haven't done that so far. So far, we're just looking at what the primary production of cells could be based on light. But now we're going to add those cells in there. Let's go ahead and save as. I'm just going to change it from primary production code to growth and nutrients. I'm going to growth and nutrients 1 code. Okay. So far this stays the same. In this assignment, we're going to learn how to read in data for the web, calculate underwater light fields using Lambert-Beer, and also compute primary production. We will also be adding in a nutrient field, probably just nitrogen only, and computing growth rates. Okay, so we're going to go ahead and acquire fields again, just like we did before, and read our sunlight data in. But in this case, we're going to be using all 10 years of data. So this piece of code here that truncates it to the first 365 days, I'm just going to comment this out. So we retain the full 10 years of data. And we're going to run our par code, converting into par, and plot that, and you'll see our 10 years of solar radiance somewhere in the North Atlantic. Think about how to put in nutrients, and those nutrients based on a mixed layer depth in the ocean. So edit my code here, and I'm going to make an object called MLD_IND, or mixed layer depth index. And my mixed layer depth index right now is just going to be 40. So I'm going to put a note here. This will change in future codes. This index will set the depth of the mixed layer, or mixed layer depth. And therefore the concentration of nutrients in the simulation. All right, so in the future we're going to make this a little more complicated. We're going to repeat the number 40 and times the number of times we're going to repeat it. It's going to equal to the length of sun time. So what's sun time again? Sun time is just this axis down here, and the length of that sun time is 10 years of data. If we just run that, it's 365.3, because there's a couple extra days in there. And here's our mixed layer depth index. The IND. All right, so it's just constant all across. So if we make a plot of sun time, mixed layer depth index, type equals O. This is the plot of mixed layer depth over time. It's just constant at 40 meters depth, right, for 10 years. Totally unrealistic, but we'll get to that. Okay, we're going to go ahead and keep our depth, creating our depth vector here, z equals minus to 100, and then I'm going to enter the, knock this down here, I'm going to go ahead and enter more code again. We're going to make a nutrient field or nitrogen field. N.field. And similar to our other fields, I'm going to make this null object. And you're guessing correctly that we're going to have a loop that fills this up. So we are creating an underwater nutrient field. And now we need an equation to relate any vector or any depth profile of nutrients. We're going to be using a sigmoidal function, and these are numbers that I more or less just made up to make it look nice. But I'm using a sigmoidal function, which you should recognize. 1 plus the exponent z plus NLD end, the xth version of that, divided by 5. That should do it. Okay, so if I say 4x in 1 to the length of par, or it could be sun time too, because it's the same length. Do this. Make this vector. So let's just do an example here. So x equals 1. So this is going to take the MLD index of the xth term, which is 40 in this case, and run it through this. Here's my z value here, which is minus 100 to 0. So if I plot now n vec versus z, you'll see a nutrient profile. So let's take a look at this. So here's z, here's depth on my x-axis, here's my nutrient concentration on my y-axis. This 0.0248, that's the maximum value down here that you get. 40 is the midpoint of this curve. That's kind of where the mixed layer depth is. And then this 5 just governs how steep of a curve we want this to be. So we could make this 50. If we run it in here at 50 and plot again, you can see it's not as curvy. If we put it in here at 0.5 and run it, we get a really, really, really sharp break. So right now I'm just setting it at 5. Of course, that could be changed, but this is just a simulation. Take our n.field, which is what we created up here, and we're just going to rbind n.field to n-vec, and that's going to be our nutrient field. So let's go ahead and run that. Okay, let's do an image.plot of sun time, our z, and our n.field. So what do we get when we image that? All right, so here's a rainbow plot showing low nutrients at the surface, high at the bottom, and our transition point here is right at 40. So this is just an example to show you what's going to happen in the next loop, but this field will be recreated in the next loop. So this is just a I'll just put this field recreated in the loop below. This is just instructive, right? And we can come back in here and you can say, well, what if I want a different mixed layer depth? What if I wanted that 80 meters? Well, that's easy enough. You just take this, run this again, and There it is. There's our index at 80 meters. There it is, right? So here's our mixed layer depth at 80 meters, which means we have low nutrients above 80 meters, high below. And so that's something that we can mess with and change in later simulations. So we'll just switch this back to 40. Let's see, I'm going to take these two fields here. We're going to build some fields. I'm just going to cut them from here and put them above here just to be clean. So here's our underwater light field. We have a primary production field. We also need to make an N field. We just made that above, but the simulation below will remake it. This will also be null. And what is this going to be? This is going to be creating an underwater nutrient field. Based on the MLD index above. All right, we need a mu dot field. What's mu? Mu is growth rate. So this object will hold the combined rate of both N and C. And what's N? N's going to be from our nutrients. Carbon is going to be from our primary production. You'll see how that works in just a minute. We're also going to have a N dot mu dot field. This object will hold the growth rate based only on nutrients. E dot mu dot field. Rate based only on C, which is carbon, which is coming out of our primary production. So it's going to be our light effect. Then we need a cell dot field. Hold the solution of the growth equation. Sum dot cell dot vec. I'll hold the So this is eventually going to hold how many cells there are in the water column at any given time, added together. K dot field now. This will hold changing mean attenuation as cell numbers change. So previously we've had a diffuse attenuation essentially kept constant, but now we're going to have it based on cell growth, and cell growth is going to be based on nutrients, and nutrients are going to be based on mixed layer depth, and light's going to be based on, you know, the sun coming up, sun coming down during the season. So this is going to be dynamic, so our attenuation is going to change, so we're going to make that not a constant anymore. Our sum dot production dot vec null. This is going to be water production. Okay. All right. So we have a couple things that we that you can see our we're going to be saving a lot more output from our model now as it becomes more complex. So these are just the holders for the things that will be saved. Are going to take this out. We don't need to set the attenuation coefficient at 0.05 anymore, so we're just going to comment that out. And what we're going to do instead is, instead of setting the attenuation coefficient constant, we're going to start with a cell population. So in previous simulations, the attenuation coefficient constant everywhere just mimicked a background cell population somehow that was producing and attenuating light. But here we're going to do it explicitly. So cell.vec is going to be our initial cell vector. Repeat, we'll start with 10,000 cells in each depth bin, times will be 100. We're going to start with 100 depth bins because we have 100 things, but our vectors are 101 long because there's one that represents 0. So we're just going to concatenate an NA on the end of this. So this is our initial cell vector that will be changed as cells grow. Okay, so it's just a constant with depth, so we're saying that at first the cells are well mixed throughout the water column. It's just going to be 10,000 all the way up to the surface. Okay, so the next thing we do, come down here and we're going to modify our Pmax values. Let's go ahead and set this at 5, at 300, and at 3. Again, you can mess with these if you want to see what happens. 4x and 1 to length of par. Now par is very long. Remember? 10 years of surface values. Our initial vector, so this is similar before, our initial value is par x, our initial value for primary production 0. Here's our Lambert-Beer law that we are computing, except what we want to do, our k vector. Actually, what we need to do is come up in here first. Okay. Let's come back up here. So let's start by making an n vector, nvec, which is just going to be a copy of what we did up here. So I'll just copy it way up here. N vector is going to be that. Okay, once we make our nutrient vector, we need to also create our attenuation vector. Let's go ahead and put this in here. K.vec is going to be equal to, oh, I got too many equals in here. It's going to be equal to our cell vector divided by a big number, 1,000,000. This is just a very rough estimation of how cell numbers may impact diffuse attenuation coefficients, right? So it basically says, as our cells grow, we're going to divide the number of cells by that to get our diffuse attenuation coefficient. That should change a little bit, but the unit is still is meters to the -1. All right. So we've got that. We also need to add a couple more physiological constraints here. So here's primary production parameters. We're also going to need, based on the Michaelis-Menten kinetics that we talked about in class, we need to have a half saturation constant for the nutrient, Am. I'm going to make that equal to 0.02, and this is in kilograms of nitrogen per day. Yeah, that's right. So what is this? This is the half saturation constant. Growth rate. We also need a NU max, which is going to be equal to 0.16. So the units of this thing, day to the -1 per day times kilogram nitrogen to the -1. So this is the maximum rate of phytoplankton based on N. And now we're going to do the same thing for carbon. We're going to make this number 0.06. Again, all of these can be messed with. This is in milligrams carbon per day, and this is going to be our carbon. This is going to be, actually, this is also just per day. I'm sorry, based on carbon. Okay, now we've got those. What else do we need to do in here? We have, so if we run this, we've created all of our underwater light fields here, or light, primary production, nutrients, mu, all those things come through here and just copy down to here. Make sure there's not any errors. Looks okay. And now we enter into the first part of our loop. So the first part of the loop creates the nutrient vector, creates the diffuse attenuation coefficient, and then we go through here and we need to modify our light equation here. So before we were treating this as a constant, but now our k values, let's just do this. Let's just do x equals 1. And then we can run this. So UI vec 38.9. Primary production vec is NA. This is our nutrient vector. K vec, K dot vec goes from, is 0.1 everywhere because we started with 10,000 cells, divide that by 1,000,000, that's what you get. But our K vec is in the same order as Z. Remember, Z goes from -100 to 0. But when we compute this thing, we need to compute it backwards from 0 going up. And the reason we have Z this way, negative going to 0, is makes it easier for plotting. So we just had to adjust this code in here that we want not K, but K vec of the Wythe term. But we need to reverse this thing. So that will flip this upside down, flip this backwards, and then we'll be able to take the Wythe term out of this. So let me give you an example here. So y equals 2. The reverse of K vec is that. So it's going to take our light value from just above, apply the attenuation vector at that depth, so it'll start at the second one, which is 0.01. That's going to compute our new light value. That light will then be pushed into primary production, which will then be stored down here. So I think this will work. So if we have y equals 2. Let's see if this works. Yeah. Dot vec. Yeah, okay, so it's decreasing. All right, good. So once we do that, and we assemble right here our underwater light field and our primary production field. So we have light, we have the amount of carbon from our primary production that we've produced over that light field. And so now we need to compute what our growth rate would be based on that light, that primary production, and the nutrient field that we generated up here, the nutrient vector. So first we're going to do it based on nitrogen. So N mu is going to equal, this is the Michaelis-Menten function now, N mu max times concentration, N vec. So this is just one number. This is a whole vector of nitrogens, divided by, parentheses again, N Km plus N dot vec. Okay, so that is the Michaelis-Menten function, and we have to add, we're going to add a loss term here. Remember how we had a loss term in our primary production? We had some kind of respiration term, and let's see if I can find that in here. Here it is, this minus R. Why are we adding a loss term here? Well, just like a cell has some background respiration using the carbon, we're going to have some background respiration using the nitrogen. So we're just going to make it 0.1 times N mu max. Okay, so again, this is just a model. This is a little bit made up. You'd want to use different values if you were doing this for real. So what are we doing here? This now relates growth rate to nutrients, in this case it's nitrogen, via Michaelis-Menten. This is a big assumption, because there's lots of different ways to relate it. Using a fixed mu max and Km, which nobody believes is actually constant, but this is just a model. We're also adding loss term. This means that N can be so low that growth rate is negative. Okay. So the next thing we need to do is do something similar, although not exactly, for carbon. Growth rate with respect to carbon. And let's see, I'll do C. I'll just copy this right from here. C mu max times our primary production vector, and CKM plus our B dot vec. Now, there's something a little bit strange that we need to do here. In this growth rate, we are allowing for negative growth rates just by subtracting them out. A growth term. In this case, we have negative values coming in from primary production already because of respiration in that equation. So we're going to have to do a little two-step here. We're going to take the absolute value. Well, let me just explain. Because of the algebra here, plugging in negative values here won't necessarily result in negative values on the other side in the way we think they're going to come out. So what we're going to do here is plug in an absolute value for ppvec on this case. So we're always dealing with positive values. And we'll go ahead and put in a quote here and here. So rating. I'll just copy this. Linking growth rate to carbon. Via Michaelis-Menten using fixed mu max and Km. All right. We are also going to compute with just absolute value, then change the sign in the next step. All right. So here's what we're going to do. I'm going to go ahead and compute. So I guess I need one more there. Okay, so what we're going to do now is when we plug in negative values here, when we have a negative primary production, we want to have a negative carbon growth rate. So what we're going to do here is do C mu where, so if we look at primary production, sorry, let's just do this. You can see it's all negative, but if we look at C mu, we see it's all positive. So what we want to do is say the C mu's where pp.vec is less than 0. So pp.vec is less than 0. That's all going to be, those are all trues. In fact, let's just put a which command in here. We're going to go ahead and put negative growth rates in their place. So what does this command do? It says wherever primary production is 0, turn that one negative and stick it into C mu. Now that should work. So let's put a note here, say, okay, a bit of a shortcut. This line makes sure that there are growth rates where there activity. Okay. Okay, so if we do this, then we look at C mu C. Yeah, okay, they're all negative now because we have negative primary production. All right, so now we need to make a mu vector, right? So we only want one growth rate to actually go into the growth equation, and we have a growth rate from carbon and a growth rate from nitrogen. So what happens when we put them together? Well, a really simple assumption is we're just going to multiply them. And put in here that this is how by n and by C are related. Nobody really knows this. This is just a, let me just put this. This is a over simple way to do this. Just a model for homework. And then we also have a little issue to work out, which is that these can both be negative, and you multiply two negatives together, they can be positive. So we're just going to amend that. mu vec, which is n mu is less than 0, and c mu is less than 0. So where those two things are less than 0, we want this thing to be 0. We want these to be where they're both negative. We don't want two negatives to multiply to a positive in this case. We want them to stay negative. So we're just going to put the negative in there, just like that. So okay. Again, this is just a toy model. Oh. And mu not found. And vec not found. Well, let's backtrack a little bit. Okay. Then we'll come down here. Oh, it's n dot vec. There we go. That was the error. There we go. All right. Now we have mu. Okay, so now we have mu vec. Okay, very good. All right. All right. So the next thing we need to do is do our growth equation. So our cell dot vec is going to equal our cell dot vec times the exponent of mu dot vec times 1. So we're just using a simple exponential. Population, assuming simple growth model. There are other models. This is just very simplified. And then we're going to say that our sum.cell vec is the concatenation of sum.cell.vec, which is an object that we already created, and the sum of true. This is storing the column. Sum.prod.vec that already exists as a null object. The sum of pp.vec equals true. This just sums all the primary production in the water column. Okay. Now we return to these guys here. I'm going to go ahead and grab these two things. I'm just going to move them down. UI field and the PP field. here's now where we're just storing our results. So before we did that with our UI field, primary production field, now we have our K dot field. K dot vec. This is what we just produced. Vec, and we can just modify these. We do n dot mu dot field. That's going to be n dot mu dot field and n mu, which is a vector. C dot mu dot field, C mu, it's got to be C field. Oh, this is going to be n dot mu dot field. Okay, and total growth rate, total fields for growth. Back in our cell field. All right. Okay, let's take a look to see what we did here. Oh, this is incorrect here, and this is reminding me of something. Let's take this reverse out here, and we're going to insert it up a little bit earlier, right after the end of the while loop. We're going to do UI dot vec equals the reverse of UI dot vec. So remember, we compute it backwards here when we do Lambert-Beer, reversing it around to compute the rest of the model, and we have to do the same thing with pp dot vec reverse dot vec. Okay. Now, what we're going to do here is I'm going to hit Control L to clear out my console. In fact, I'm going to do remove that just to make sure everything's cleared out, clear my plots using that little button there. And I'm going to go back up to the very top, make sure everything is good. There we go. Run it just to the beginning of the model there. This is going to compute our sort of test nitrogen field for us first. Right, now we're going to compute the model all the way down to the end of that one. There we go. Okay, run. So it's going to go quickly first, step through the days rather quickly, and then as it starts storing more and more information, remember we're filling all those fields with data, it's going to start, the computer's going to start to slow down a little bit, so we have to be a little bit patient. All right, let's now plot one of these underwater light fields and see what it looks like. Okay, so here we go. We have this year, looks like we have light penetrating deep, and it's not penetrating as deep, but it's still plenty bright up here on the surface. That's pretty interesting. So we can do a couple more exploratory plots here. So let's plot UI.field 1, comma. This is the first row in UI.field that represents the first time period. Z and our xlab equals light, ylab equals depth. Let's do main. First time period. So if we plot this, this is now UI field underscore 1. I apologize. Okay, you can see decreasing light with depth on January 1, 2005. So that's right in the beginning of the simulation. So we still have plenty of light making it to the bottom, which is similar. If we hit this little back arrow, it should bring us back to our previous plot. Yep, right in the beginning of the simulation, plenty of light going down. Now let's say change this to the 900th time step. And we can see definitely something going on there around 40 meters. So it's still Lambert Beer, but it doesn't look like an exponential drop anymore. Same equation, so there's something different going on. And let's try 1800. Yeah, even more. Okay, so let's now take a look at primary production. All right, so primary production, we have some interesting sort of saddle features here. We have the highest values kind of in the right here and then down. So we have low when in the surface when it's the brightest. That's probably non-photochemical quenching. And we have low when there's no light. And then we have these saddle features. That's pretty interesting. That means that what if we did a plot of let's just copy this. This is our c.mu.field. So this is now making a color image of the growth rate with respect to carbon. Yeah, very similar. Okay, so where we've got plenty of light, we have positive growth rates, or we have no light, or light's too high, we have low. And let's now take a look at maybe growth rate with respect to nitrogen. And what do you think this is going to look like? Yeah, looks just like the nitrogen field, right? Low up top, high down on the bottom. So if we make now a color image of the growth rate, total growth rate, just mu field. Yeah, okay, so we get an interesting pattern here. Close to 0 up here on the top, some positives, that's probably low nitrogen. We have high nitrogen down here, but that only works if we have some light that's actually getting down there. So that's leading to an interesting growth pattern, which means that what happens when we make color image of the cell field. So this is the number of cells that have actually grown. Yeah, so you can see the cells showing up right at around 40 meters. Right there, right at the interface of where we have light and nutrients. Now the rest of this code down here from our previous one you can probably get rid of. And I'm going to point you to the homework to explore these plots a little bit further.